scheme I've got in place. Depends on the magnitude of the change. And here's a common X-bar chart. This is an X-bar chart set up at plus or minus 3 sigma with an accurate evaluation of sigma. Right? This is what, here's our average run length at 0. Right? Our fault signal rate is 1 in 370. Right? And it starts to drop off. Right? So this is an average run length for a common X-bar curve for an X-bar common X-bar chart. Notice that this chart's primarily a chart for detecting process shifts. An X-bar chart is trying to detect shifts in what? The process mean, right? That's what it's trying to detect shifts in. Right? The fault signal rate, or the ARL at 0 here, no shift from target, right, is 0.0027. 1 over that is 370. Okay? Now, you can see it's sensitive to shifts that are greater than or equal to about 2 standard deviations of your sample average, right? Right in here, right? Now it's going to take us about 6 observations or so, on average, to pick up a shift of about 2 standard deviations. Okay? Notice it's not so great for a 1 standard deviation shift. It's going to take us about 40 observations to detect it. Okay? Larger shifts, good for picking up large shifts. That's what Shewhart type charts are designed to do. Okay? And there are other alternatives to picking up smaller shifts. Now, you can also do average run lengths for S charts. And I'm going to introduce it here because I'm going to talk a little bit about variation before the talk is over. You can do it for S charts as well. Right? And usually what we're looking at here is increases in variation. Right? So what we do is we look at the change being in the ratio of the current process variation to what's expected, okay, or the in-control process variation. And as that ratio grows, right, you'd like to be able to pick it up. It's primarily used for, again, is detecting increases in within-group variance. Okay. It's sensitive to within-group standard deviation changes of about 50%, right? About 50% increase in your standard deviation is going to be about, what, 11 or 10 or 11, right? Observations before you'll be able to pick it up. Okay. Okay. So how do these overall false signal rates and sensitivities compare for some of these control schemes I've talked about? Well, the problem is really difficult if we try to incorporate this movement, this periodic movement, right? So it's a lot more tractable if I just say, okay, I'm going to set the control limits. I'm not going to move them. Let's look at what my average run lengths are there. It's still valid because it's only going to get worse, right? They're only going to be larger as you start to move your limits as your process moves, okay? This is the chart I just showed for a common plus or minus 3 sigma X-bar chart, right? 370 kind of works its way down. Right? Notice it's on a log scale over here, as it was before. If I use a 2 out of 3 rule with plus or minus 3 sigma limits, well, yeah, I reduce my false signal rate significantly. What's that? 1 in 600 or 60,000, 70,000 almost? 1 in 70,000 false signal rate versus 1 in 370. Okay, probably a good thing. Right? Unfortunately, I've got this problem out here though. Right? It takes me 4 times as long to pick up a shift of 2 sigma. Right? And this is if I don't move my limits. Okay? If I don't move my limits, if I keep them fixed. Right? It still takes me 4 times as long here. It takes me about 3 times as long here. Okay? So you reduce some sensitivity. And if you're interested in 1 sigma shifts, you're pretty much out of luck. 1,000 observations. You just don't have process runs out there. Okay? If you do use a plus or minus 2 sigma limit, your average run length curve does something like this. Right? The false signal rate is a little higher, right? A lower ARL 0 is a higher false signal rate. You could adjust it so that you make it the same or larger, but you get a little better sensitivity in here. Right? You've cut this one pretty significantly for a 1 sigma shift. For a 1.5 sigma shift, you've cut it from 15 to about 10, about a third, right? In terms of time or product at risk until you detect this issue. Okay? So 2 out of 3 rules are not bad rules if their limits are set up correctly. So, some consideration. probably want to focus your SBC efforts on the critical parameters. Right? Most organizations I've worked with, right, do more than just the critical parameters. They get an automated system, they apply it to everything, right? But that's just an approach of ignorance, right? It's a shotgun approach. It's an approach of ignorance because it's saying, I don't know enough about my process to identify the ones that are critical. So I'm going to throw it at everything, right? It's a big issue that I've seen in application of SBC. It leads to disillusionment with the process, with the system, because you just can't manage a system that big, right? You generally don't have the resources to be able to manage it, especially if you've got a limited set of personnel to respond to all those signals, right, every day. Yeah? So bite the bullet, know your process well enough to pick the critical parameters, do a good job with those, right? If you just try to do everything, you end up doing a mediocre to poor job with everything instead of a good job with the things that count. I mentioned this already. And if you're going to do, if you're the ones you get picked to control the target. Pick a target and control to it. Okay? Center your control limits at that target value. Don't use the process average, right? If you want a target value, try to drive your process there. Okay? The fact that the process average is out there is information that you're not where you want to be. Okay? And leave them centered there. Don't move them. Right? It doesn't make any sense. Move them around. Okay? Kind of defeats the entire purpose. If you want to periodically recalculate limits, that's fine. But you kind of want to limit that to re-estimation of the variation, re-estimation of sigma. And you might want to be a little careful when you do that. Right? Okay? You've got to be aware of, when you redo that, is there assignable cause variation in that data stream you're using? If it is, you're going to get an overestimate. Obviously, if you have a major process change, then probably recalculation of limits is appropriate. Choose a multiplier for sigma that makes sense for the operation. Right? Just blindly throwing 3 at it, that's maybe a good thing, maybe not. And I'm going against really strong history here. Short said 3. Right? Deming said 3. Right? So I'm kind of going against some of the gods here when I say this, but Short and Deming worked in environments that are not the same as what we've got today. Find a tolerable false signal rate, something you can live with. Okay? Have appropriate level of sensitivity. Right? Example that I like to suggest is an example I worked with at a semiconductor company where they measured thickness of an oxide, and they found out that they could detect changes of about 20 angstroms, right, in their process. Shifts in the process of about 20 angstroms. The control that they had on the process was time, right? And time they could only move in second increments, right? So when they moved it, they knew when they moved the process by a second, they changed the thickness by 50 angstroms. Okay? So does it do any good to detect a 20 angstrom shift? Probably not. Okay? Probably want to detect a larger shift, right? So set your sensitivity relative to the situation. And it is going to depend on the constraints. Right? Your tolerable false signal rate oftentimes will depend on your personnel as well. Right? You're likely going to have to consider average run length curves when you do this, right, if you're going to do a good job of it. Now, I mentioned that SHUAR is not real sensitive for smaller shifts. Right? There are other approaches that are, like EWMAs, Q-sums, run rules, right? Things like that. If you're going to do those, you've got to make sure that you're going to commit to manage them appropriately. Right? You got to have, they take a little more management, right? They're a little more powerful, but you got to have the commitment to manage them. And be willing to admit that there are a lot of parameters that you're just monitoring. Right? Monitoring is not control. Right? Okay? Control means you're actually acting on the process when you get a signal. Monitor means, well, you get a value and it maybe didn't make you feel very good, or maybe you hold product. Holding product's not working on the process, right? So control is a lot stronger than